Okay, all right, all right. Hello, guys. So we are moving right along, and our last unit, or I'm sorry, our last lesson for this unit in Chapter 2A, it's called Implicit Differentiation. So um, the last thing that we kind of left off with is kind of learning about the second derivative, and again, just exploring different ideas with that. Today is all about just a new approach to derivatives. Okay, so I got a little bit of a warm up here, just reviewing, taking the derivative of a specific function, finding the second derivative here in number 2. We can do those together in class tomorrow. We can also go over this worksheet again tomorrow if you'd like. But again, the answers are in the notes from yesterday. Okay. All right, now jumping into today's stuff. So let's start off by thinking about this. All right, this will introduce the idea. It says find the slope of the tangent, which we know what that means. It's just derivative, on a circle centered at the origin. So we're looking at a circle centered at the origin with a radius of 5 at the point 3, 4 on the circle. So let me kind of draw that out real quick. So we got this circle. Okay, it's centered about the 0, about 0, 0. And it's got a radius of 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Wow. Okay. So there's my circle. Now, it says that the point 3, 4, which is about right here, okay, about right here on my circle is, and it wants me to figure out the slope of the line tangent right there at 3, 4, which we can already kind of tell is going to be a negative answer. Okay, but it wants to know the slope there. So in order to find this derivative, let's think about what the equation of this circle is, and hopefully it kind of comes back to you a little bit. Remember that the general equation is x minus h squared plus y minus k squared equals r squared, where h and k are the center and r is the radius. So hopefully that kind of refreshes you on that. But since h and k are both 0 and the radius is 5, this is going to be x minus 0 squared plus y minus 0 squared equals 5 squared, which is 25. Okay. Now, I got the point 3, 4, and I'm trying to figure out the derivative of the slope there. So we got to take the derivative. Right? Well, how do you suggest taking the derivative at the point 3, 4? And notice how it's not y by itself. Okay. So thinking about it, and if you're sitting here processing how to take the derivative of this, you're probably thinking, well, let's get y by itself. So let's see what happens. We get y squared equals 25 minus x squared. And then if I take the square root of both sides, I get y equals plus or minus the square root of 25 minus x squared. Now I want you to leave some space to the right because we're going to come back to this problem. Now we got y equals plus or minus the square root of 25 minus x squared. So how do you take the derivative of a plus or minus? See, that's kind of the issue that we run into. Now, I'm sure some of y'all are probably thinking, well, do we even need the minus part? Because the point that we're curious about is the top section of my circle. And if I'm looking at the top section of my circle, all I need is the positive square root. So what we're going to do is we're going to say y equals just the positive square root of 25 minus x squared, because it's that portion or piece of the graph that contains the point 3, 4. And we can take the derivative of that. So y prime is going to equal, not y squared, y prime is going to equal. Remember, the chain rule says to bring down the power of 1/2. We leave the quantity inside the fraction untouched, and we're going to subtract 1, so it's going to be negative 1/2. And then multiply by the derivative of the inside, which is negative 2x. So that's derivative using the chain rule. And if I want to plug 3 into that equation for x, I would probably write it this way. I'd probably put like negative 2x on top, and on bottom have 2. And then this comes to the bottom of the fraction. It just helps compute it a little bit quicker. Okay. which the 2's cancel. So that's going to end up being what? -3 over the square root of 25 minus 3 squared, or 9. And I believe that's the square root of 16, which is 4. All right, well, that kind of makes sense. I mean, the slope is negative, and we already determined earlier in the problem that the slope was probably going to be negative. So I figured out that the slope at 3/4 is -3/4. And how we did that is a little bit of logic. We just got y by itself and thought about between the plus or minus which one we needed to use. Okay. So keep that problem in mind as we go to this next slide. We're going to come back to this slide in a second. Okay. Nothing terribly new yet. All right. Here we go. So implicit versus explicit. This is the new part. It says an equation like y equals the square root of 2x plus 1 is called explicit because it describes describes one variable in terms of another. In general, y equals f of x is explicit. So if I say explicit, it is a y equals equation. It is one variable described in terms of another. So like, y equals is explicit. Now, for instance, the equation y plus the square root of, or x plus the square root of y equals 1, that equation is not explicit. It is not one variable on one side equals another. This defines y as a function of x implicitly. Okay? Whenever both variables are intertwined in the equation where it's not explicitly x equals, we call that implicit equation. Okay? Now, a lot of times, well, actually, sometimes you're able to get an implicit formula in terms of an explicit formula to take the derivative, much like we just did in the last example. Okay, and you can kind of see right here, like this is the implicit formula right here. Okay, this right here is implicit, and all we're doing between these two steps is solving for y. Okay, and then we were able to get the function. Okay, we were able to get the function in an explicit form. And now the function is defined explicitly. So if I ask you to take the derivative of that, for instance, you would just do y prime equals, and you do chain rule. 1 minus x to the first power, and then times the derivative of the inside would just be the derivative of negative x, or negative 1. And you have your answer. Okay. And you could probably simplify that a little bit. That's actually not too terrible. What would happen if I simplify that? -2 plus 2x. But anyway, so that's great and all, and you can do that. But sometimes, all right, sometimes the issue is that we're not able to get y by itself. Sometimes it's kind of ugly. Sometimes there's a plus or minus, or sometimes we have multiple y's in there, and it's impossible to get y by itself. Okay. Now, implicitly, let's discuss how we would take this derivative. I mean, in this case, we could solve it explicitly, which is fine. But let's talk about how we would do implicit differentiation. Okay. So the equation is x plus the square root of y equals 1. Okay. If I ask you to take this derivative implicitly, it means that we're not having to get y by itself. Let me explain. We're going to take the derivative of each piece. Okay. The derivative of x we know is 1. That's fine. And actually, I'm going to write it this way. Just this one time to help us see it. Okay. We're going to take the derivative of each piece. So I'm clearly showing you we are taking the derivative of each piece. That's what it means to do implicit differentiation. Now, we know the derivative of x is just 1. Okay. We are taking the derivative with respect to x. That's what that notation means. So any other variable that I have to take the derivative of, we take the derivative of that implicitly. And how that works is pretty much just an application of the chain rule. I'm going to take the derivative of this, no problem. The derivative of y to the 1/2 is 1/2 y to the negative 1/2. But then I'm going to multiply by the derivative of the inside. Okay. Now, normally if I were doing power rule, the derivative of the inside would be the derivative of x, which is 1, and it goes away. But the derivative of y is not 1. The derivative of y is just y prime. I don't know what y is. I'm just going to call it y prime. Another way that we write that with implicit differentiation is just dy over dx, which is another way of saying y prime. And the derivative of 1 is 0. So there you have it. That is the derivative implicitly. But there's one extra step you got to do, and that is getting dy over dx by itself, which is y prime. Okay. So all I'm going to do is subtract 1 to the other side. And then I'm going to divide by 1/2 y over negative 1/2. Okay, so I get dy over dx, my computer's having that lag again, darn it, equals -1 divided by, and I'm going to say 1 over 2 to the positive 1/2 power, or just square root of y. Which if I end up just doing same change flip on that, I get dy over dx equals, and that's going to end up being negative, same change flip with negative 1/2 over 1/2 would be -2 square root of y. Now, I know it may be hard to tell, but these two equations are equivalent to each other. Okay, one is just in terms of x on the left side, and the other one's in terms of x and y, which in this case is just y. But they are saying the exact same thing. I mean, if you think about it, if I plug in what the y equation is into this, so look at this. If I do -2 and the square root of y, well, y was just 1 minus x quantity squared, which is what we figured out up here. If I simplify that out, the square root of squared goes away, and I'm left with -2 times 1 minus x, which is the same thing as that function above. So they're both the same derivative. They're just in terms of different variables. One's in terms of just x explicitly. The other one may have x and y in it. Okay, so keeping that in mind, let's go back up to this equation here. Remember this one that we solved? It was x squared plus y squared equals 25, and we solved for y in order to do that. Well, let's see what happens if I do this implicitly. So we got x squared plus y squared equals 25 as my original equation. Now, if I take the derivative of 2x, or x squared is 2x, and the derivative of y squared is 2y, but you got to multiply by the derivative of the inside. A safe bet is if you're taking the derivative of y implicitly, always tack on after you're done with the derivative, the dy over dx, or the y prime, because that's essentially what you're doing, is you're multiplying by the derivative of the inside, and we don't know what the derivative of y is, so we say dy over dx equals 0. All right, now if I'm trying to figure out what the derivative is, we got to get dy over dx by itself, because that is what y prime is. So what I'm first going to do is I'm going to, I'm sorry, that should be a y. Subtract 2x to the other side and divide by 2y. So -2x divided by 2y, which is just equal to -x over y. So that right there is my derivative function. Okay, that is my derivative function implicitly. It's in terms of x and y, but it still will give me the same answer. Okay, notice all I need is the point x and the point y. I actually need that other point to help me with this derivative. So dy over dx equals -3 over 4, which is the same exact answer that I got down here. But notice how it required a lot less steps. So implicit differentiation can sometimes be a very beneficial thing, okay? Especially if you don't have y by itself and you don't really want to, all right? Okay, let's put some steps there. So implicit differentiation is a technique used to find the derivative of an implicitly defined function, okay? So just things to keep in mind here. You're going to have x's and y's, or multivariables. It could be anything, as long as it's more than one variable. Okay, and it's a situation wherever y is not isolated. It's not y equals isolated. All right, let me give you the quick little steps here to this. All right, step one. All right, you're just going to take the derivative with respect to x on both sides of the equation. I'm going to type this out. It's faster for me to type. So you're going to take the derivative with respect to x. Okay, with respect to x on both sides of the equation, which is what we did earlier. We took the derivative of both sides with respect to x. Okay, that's step one. Now, step two is going to be, and whenever I say in step one, take with respect to x, that means if you ever taken the derivative of y, you put the dy over dx by it. And step two is the last step. All you got to do is just solve for dy over dx. You solve for that. Or another way of saying that is just y prime, if possible. Okay. Sometimes it's not going to be possible to solve for dy over dx, and you'll see situations like that later. Okay. All right. So we've just shown two examples of that already in these last two examples. Let's do a couple more. Maybe I'm definitely going to save this. What time is it? We're 17 minutes in. I'm going to save the last two for notes tomorrow. And I'm going to do maybe these four with you right now. Okay, and then I'll call it. Okie doke. So we got find dy over dx implicitly. Now this is a perfect example here. I mean, I got x squared y cubed equals 2x plus 1. I guess I could divide by x squared and take the cube root. But again, you're not always going to be able to get y by itself, especially if I have more than one y in the problem. So let's just do this implicitly. Okay, so I got that, and I got this equation here. Let's take the derivative of the left side. The derivative of the left side is going to be the product rule, because we got two things being multiplied together. So it's going to be the derivative of the first. The derivative of x squared is 2x, and we're going to leave the second one the same, plus keep the first the same, and the derivative of y cubed using power rule is 3y squared multiplied by dy over dx. It's like taking the derivative of the inside, and the derivative of y is dy over dx, or y prime. On the other side, the derivative of 2x is 2, and the derivative of 1 is 0. Okay. So there you go. Now, that's step one, is taking the derivative with respect to x. Now, step two is getting dy over dx, which in this case is just this, by itself. All I'm going to do is subtract this quantity to the other side and divide by this quantity. So what I'm left with is dy over dx equals 2 subtract 2xy cubed, and then divide by the quantity x squared 3y squared. So what we did is we just found the derivative, all right, of this equation with respect to x. Now we left y in the equation, and that's okay. B is actually what we we already did B. 2x plus 2y dy over dx equals 0. Yeah, we've already done this problem. So dy over dx equals negative 2x divided by 2y, which is just negative x over y. All right. It's not too terrible math, I don't think. Let's do a couple more. I'm at 20 minutes. I won't end at 30 minutes, but yeah, we'll do these two later. Okay, you're welcome to try both of these. You're welcome to try the second derivative and the slope where it's horizontal, but we have to do a little bit extra for each of those, but you're welcome to try them. Okay, the derivative of 2x is 2 minus. Now, we got x times y. That is product rule. We have one variable times another variable. So how we take that product rule is we're going to do the derivative, and I'm going to do all this in brackets because we got this minus right here. The derivative of x is 1, and I'm going to leave the second one the same, plus leave the first the same, and the derivative of y is also 1, but 1 times dy over dx. Okay. And then plus 3y squared dy over dx, and the derivative of 20 is 0. Okay. Now, the only difference in this case is that we have 2 dy's over dx's. So we're going to have to do some factoring here. First of all, let's distribute the negative. So I got 2 minus y minus x dy over dx plus 3y squared dy over dx equals 0. Now, since we have more than one dy over dx, it's going to take one extra step to get dy over dx by itself. The first thing is to get these quantities, okay, to one side of the equation. So what I'm going to do is I'm going to move both of these, and it really doesn't matter which ones. I'll move both of them over here. How about that? As long as they're on one side. So I'm left with 2 minus y equals, that's going to be positive x dy over dx, and negative 3y squared dy over dx. Now, the idea is to get dy over dx by itself. So if you notice on this whole side, they all have a dy over dx in common. So I'm going to factor that out. And what I'm left with is x minus 3y squared. And I still got 2 minus 1. So I think you can kind of see the point of doing that is that we now just got a dy over dx from being 2 down to 1, and I can solve for dy over dx now. I can divide both sides by x minus 3y squared. What do you think? Not too terrible? Okay. One more. So I got sine of x plus y equals y squared cosine of x. Let's take the derivative of each. So on the left-hand side here, we have the derivative of sine on the outside and a quantity of x plus y on the inside. So the derivative of sine is cosine. I'm going to leave the inside untouched. And then multiplied by the derivative of the inside. The derivative of the inside is 1 for x and 1 for y, but with a dy over dx attached to it. Okay. That's going to equal, all right, y squared cosine of x. So again, that's going to be product rule. So it's going to be derivative of the first, which is 2y dy over dx, and leave the second one alone, plus I'm going to leave the first one alone, and the derivative of cosine is negative sine. Okay. So let me try to write this a little bit nicer. okay? And if you notice, again, I have dy over dx's, two of them. So I'm going to have to probably combine them somehow together on one side and take out a GCF. So I recommend doing that by, first of all, distributing this value through, like go ahead and distribute everything out, and then we're going to get all the dx over dy's or dy's over dx's to one side. So right now on this side, I got the cosine of x plus y plus the cosine of x plus y times dy over dx. My goodness gracious. Okay, so the cosine of x plus y plus the cosine of x plus y times dy over dx when I distribute that, and equals 2y dy over dx cosine x, and I'm going to say minus y squared sine of x. Okay. So now, if you see, everything's distributed out, and I got this term with a dy over dx and this term with a dy over dx. And I'm going to get all those to one side. So actually what I'm going to do is I'm going to bring this one over here, and I'm going to bring this quantity over here. So everything's on the same side. Okay. So on the left side, I'm going to have cosine of x plus y dy over dx. And now I'm going to have minus, and I'm going to write it as 2y cosine of x with dy over dx attached to it equals, and on this other side, I'm going to have negative y squared sine of x minus cosine, I'm going to try to squeeze it, x plus y. Okay. And now what I'm going to do is I'm going to take out a GCF of dy over dx out on this side, and then divide both sides by what's left over. I'm going to try to do this in one step for the sake of time. Dy over dx equals, I have negative y squared sine of x minus cosine of x plus y on the right, and I'm dividing that by cosine of x plus y minus 2y cosine of x. All right. Now, that was a doozy. That was a good one. That was a hard one. See, that was one example where we couldn't get y by itself no matter how hard we tried, and that's why we had to do implicit differentiation. So try those out. If you want to try those too, you can, and there's the homework. Otherwise, I will see y'all tomorrow and finish this up tomorrow. So good job today, guys, and appreciate all y'all do.